So, good morning everyone. നമ്മൾ canonical ensemble നെ കുറിച്ചാണ് ഡിസ്കസ് ചെയ്യുന്നത്. So today we are here to discuss about canonical ensemble. So in our last class we were discussing about micro canonical ensemble, and there are two examples as harmonic oscillator and classical ideal gas cases. So we have explained the harmonic oscillator and classical ideal gas using micro ensemble canonical ensemble theory. Okay, so we know that micro ensemble case, so that is micro canonical ensemble. So I can write it as micro canonical ensemble. Okay, so in that case we'll actually the parameters. So what is ensemble is? Ensemble is a large collection of different microstates within a macrostate. So each microstate will have a definite number of particle, volume, and corresponding energy as well. Okay, so this will be fixed energy, number of particle and volume will be fixed. And also when we discussing microcanonical ensemble, we understood that the energy is not a fixed one, because this have a particular energy interval we will be treating, that is E minus delta by 2 and E plus delta by 2 as the two energy interval. So we are considering the Hamiltonian between E minus delta by 2 and E plus delta by 2 in the case of microcanonical ensemble case. So basically a microcanonical ensemble, it is giving an idea of number of microstate or number of representative points in that case. Okay, so when you consider a microstate, okay, so microstate basically giving an idea of the number of particle and volume energy within that regime. And also when you consider microcanonical ensemble, where we also interested in the particular energy interval delta as well. Okay, so in the last discussion we have identified, so we are interested only in the area that is delta. So where we'll be having the phase space, where we'll be having representative points you can found on the particular energy interval delta. So once you get the microstate, okay, then you can easily find out at the thermodynamic relation corresponding to that. Okay, so once you get the corresponding gamma, then you can directly put into S is equal to kb ln gamma, and from that once you get the entropy. Okay, so once you get the entropy, then you can actually derive the different relation of thermodynamic parameters like pressure, temperature, energy. So different parameters you can derive in this case. Okay, now when it comes to the discussion of a microcanonical ensemble, so all the physical state cannot be explained by microcanonical ensemble. Okay, so some physical states are difficult to, okay, some physical states are difficult to explain by our microcanonical ensemble case. Okay, so why that? So why we cannot explain? So it is difficult to explain some physical state. Okay, so the main issue in that case is that there are two reasons that is mainly addressing, that is we cannot actually exactly, we cannot measure the energy associated with the any cases. So here you can see, you know that in the microcanonical ensemble we are actually dealing with the fixed energy, okay, or a interval energy, right? So we'll be dealing with that in microcanonical ensemble case. Okay, so the main issue with the energy is that, so you cannot find the total energy. Okay, total energy of a system is difficult to measure. Okay, so we cannot exactly measure the total energy of any system. Also it is difficult to keep the values of energy or any parameter, okay, under a restricted under a restricted physical control. Okay, so it is difficult to control the energy flow or energy exchange in a system, so it is very difficult to identify the total energy of a system to be measured. Okay, so while considering these two aspects, because you cannot exactly measure the energy of any system, and also we have a difficulty that, so it is difficult to keep the value of energy in a fixed control or a strict physical control. You cannot exactly control the energy of any system. Okay, so in the case of in the case of microcanonical ensemble, we mainly treating this as what? So where we are treating this as in a fixed energy or a particular energy interval. So while coming to canonical ensemble, okay. So while come to canonical ensemble, so here we are treating in canonical ensemble case, instead of instead of energy interval or fixed energy, we actually take the representation of, okay. So what we do that, instead of fixed energy or energy interval, we fix the temperature of the system. Temperature of the system. Okay, so that is more convenient uh, than if you control the energy representation of the corresponding case. So in that case, so what I say that what is a canonical ensemble is that, so it is an ensemble, okay, it is an ensemble in which the macro state of the system is defined by NVT. Okay, NVT, so which is called canonical ensemble. Canonical ensemble. Okay, so in an ensemble case where we'll have a fixed number of particles, fixed number of volume, and fixed number of temperature, instead the fixed energy. So here these are the three parameters actually give the idea of the microstate of a canonical ensemble case. So such a different microstate will form a macrostate. Okay, such a large collection of such macrostates are called an ensemble corresponding to this case. Okay, so here number of particle, volume, and temperature are the different fixed values in a canonical ensemble case. So what is ensemble is? Ensemble is a large collection of macrostate, microstate within a macrostate, or it is a Mendel copy of different state as well. Okay, now in order to understand it, let me introduce you something, because where in that system there should not be any exchange of energy, okay, or the exchange of energy will not be limited, where you can limit the temperature will be constant in this case. So let me just take an example of a heat reservoir. Okay, a heat reservoir. Okay, so what is a heat reservoir? Is the heat reservoir is an infinitely large thermal capacity or heat capacity will be there, for which possess infinitely large thermal capacity. So if you add or extract any kind of any value of temperature from the system, so there will be no temperature variation for a heater reservoir. Okay, So in the heat reservoir which have infinitely large thermal capacity or heat capacity, okay. So in this case, so if you add or extract any temperature from that heat reservoir, there will be no change in the temperature for a heat reservoir case. So let me just consider a heat reservoir like this, and I put a system. Okay, so this is my system. Okay, so this is our heat reservoir, and within the system there will be a temperature, and heat reservoir also will have temperature. And also we can say that this possesses an energy that is er, and this heat reservoir possesses an energy er dash as well. Okay, and here the possibility is that 0 to er, so it can actually, or 0 to infinity, so up to 0 to infinity it can exchange the energy. Okay, so in this system the system can exchange energy from 0 to infinity, whereas the temperature will be a constant one for the all cases. Okay, so that is the main thing we will be addressing here. So that is the main idea of introducing a heat reservoir also. Since it's having a thermal capacity, so any change in the system, any change corresponding to system does not alter the surrounding condition of the system. We can just assume that this heat reservoir is a macro state, and this system is a one of the microstate in that one. Okay, so whatever the change that is coming outside or surrounding to the system, there will be no temperature change, because this is we are treated as a heat reservoir, means which having an infinitely large heat capacity. So whenever you add or extract any temperature from that heat reservoir, it does not change its temperature, so the temperature remains constant throughout the period of time. And in this situation we can say that the temperature is controlled. Okay, so by putting in a heat reservoir, the temperature is basically what? It is a controlled environment. So temperature as a controlled environment, whereas the energy can exchange from 0 to infinity. Okay, so let me just take a case that is at time t. So let we say that system possesses energy that is er. Okay, and reservoir possesses an energy that is er dash. Okay, and now if I want to find the probability of finding the system's energy, okay, so then I have to find the PR corresponding to that. So what is ER and ER dash means? So after a time, that is after a thermal equilibrium, or at a point of time t, the temperature of the heat reservoir, so the energy of the heat reservoir is ER dash, and ER is the system's energy representation. So from this representation one can actually find the representation of a probability of finding this micro state or this particular system. Okay, and its corresponding energy as well. Okay, and what is happening is that, so the as time travels, system having possessing an energy er, and reservoir having energy that is er dash, that is what we are seeing here. Okay, now let me just introduce you a macro state condition, because when we discussed about ensemble theory, so we have a macro state, so that is we have taken like this. Okay, okay, so in this case this is a microstate with nvt as the uh, corresponding parameter. So this is a canonical ensemble case. Okay, canonical ensemble case, and here these are different microstate nvt with the number of volume and number of particle, volume, temperature will be fixed. Okay, so that is nvt, and similarly nvt, nvt, Vt. Okay, so this is the representation in this case. Now, as I said, we have a representation of a system that is kept in a heat reservoir. And similarly, you can also explain here, you consider the central microstate. This is central microstate. Around this central microstate, there are other different microstate. Okay, so this entire one that is surrounding to this red box we can treat as the macro state outside this micro symbol micro state. So this you can actually consider as a system. Okay, and entire this portion, this NVT, entire this portion you can actually consider as a what? You can consider as a heat reservoir. Heat reservoir, like you can actually assume. So it is similar like you considering this as a heat reservoir and this is a system. Okay, now what we need to identify is that the probability of finding the energy of this particular microstate. Okay, the probability of identifying this particular microstate, that is we have to identify, and the corresponding energy of this microstate also we need to find it out. Okay, so whenever you do that, you'll be actually getting the number of microstate corresponding to that as well. So let me just say that the corresponding microstate, let me introduce as omega, is the microstate, and we'll have a number of identical microstate that is surrounding to this particular region. Okay, so we'll have number of particles corresponding to that as well. So let me introduce epsilon is the energy of ER dash after a time interval. Okay, so ER dash is, I can take it as equal to epsilon, where ER dash is the energy of the heat reservoir and epsilon is obtained after a thermal equilibrium. So what we will do here is that we'll have ER, the energy of this region is ER, and corresponding to this entire surrounding will be ER dash is the corresponding energy of that one. Okay, so it is similar like you are putting a system in a heat reservoir situation. Okay, now if I want to identify the energy or the probability of this one, and the probability will be equal to, it is proportional to gamma, where gamma is representing the microstate. Okay, microstate. Okay, which possessing the energy ER dash. Okay, so whenever you find the probability of this ER, you are actually taking the, it is proportional to the microstate that is surrounding to this particular region. So that's why we take it as in terms of omega dash ER dash, because here we are considering the microstate outside to this small microstates. Okay, so that's why we will be the probability of identifying this, we can say that PR proportional to omega dash ER dash. Okay, so in order to find probability of finding this particular region, so which is actually proportional to finding the number of microstate outside to that particular system. Okay, or rather we can say that it is the number of microstate that is around that, the energy of the microstate. So it is actually the probability is directly relating to the energy of the heat reservoir or surrounding microstate to that particular microstate region. Okay, so this is the equation that is we further will be examining. So I can say that, so we'll have two consideration here. The first one is that the system is in equilibrium. System in equilibrium, okay, with the reservoir, with the reservoir at a common temperature. Okay, at a common temperature T. Okay, and and we can study the statistics of the energy exchange between system and heat reservoir. Okay, so this is the one method we can identify the probability of this case. And secondly, the second method we can adopt is that the system as a member of a canonical ensemble. Okay, canonical ensemble. So where which having n v t as the corresponding values, in which energy epsilon is being shared by the n identical system. Okay, an identical system constituting ensemble. Okay, so as we have seen the ensemble representation. Okay, constituting ensemble, and studying the statistics of statistics of this sharing process. Okay, so there are two ways you can actually find the probability of finding the energy of that system. Okay, probability of finding the energy of energy exchange between the system and heat reservoir, that you can study. Okay, and the second one, that is what we have said in the first case. Okay, so this is the first case we can do one way, and the second case is this one. Okay, so these are the two cases that I have written here as well. Okay, so in these two way actually you can measure the corresponding value associated with that. Okay, now actually we are following the second method. Okay, so in order to find the probability we will be following the second method, that is more convenient, because where we can actually take the consideration of canonical ensemble representation in order to evaluate that. Okay, so here, so we will be evaluating the equilibrium between the system and reservoir. Okay, reservoir. Okay, so this will take as a condition, then we will evaluate the corresponding probability of finding the energy, probability of finding the system represented here. So let me just consider that I have a system which has a representation A, and A dash is the surrounding heat reservoir or the surrounding macro state. Okay, which having Er dash as the energy, temperature is T, and inside the system will have A and Er and T. Okay, so let me just represent it, that is here. Inside the system will have A, Er and T as the temperature. So temperature is common in this case, and where A dash is the reservoir and A is treated as the system in this case. Okay, then we can say that the at equilibrium or at E0, so we'll have the energy will be equal to Er dash plus Er. Okay, so that is equal to a constant. So at E0, that is initial case, Er dash plus Er equal to a constant, and now from it is traveling from 0 to E0 dash, that is into the almost the equilibrium state. So at the equilibrium state we'll have ER dash plus ER. Okay, so it is the energy exchange from 0 to E0 dash. Earlier we represented 0 to infinity. Now we are limiting at a case that is 0. The exchange energy exchange is from 0 to E0. Okay, and now from this equation we can represent that ER is very less than ER is very less than uh, E0 case, because E0 means ER dash plus ER, and where ER is actually representing the energy of the small system. It is, so it will be very comparably very small, right? So we can say that ER is very less than E0. Okay, and since that we can say that uh, ER by E0. So in that case we can say that it will be very less than 1. Okay, so we'll have a small microstate with having energy ER and a reservoir ER dash. So at equilibrium we'll have a temperature that is ER dash is equal to ER, so which is equal to a constant. Okay, so at equilibrium what we will be having, ER dash should be equal to minus ER, then only we'll be having correspondingly it should be come to an equilibrium. Okay, now in the above session we got a representation corresponding to the probability. Okay, for probability of finding PR, so that is equal to PR is proportional to what, it is proportional to omega dash ER dash. Okay, so that is proportional to omega dash ER dash means what, so that is E of 0 minus ER. So I can write like this, right? And now if I take the logarithmic on either side, I'll have ln PR that is proportional to ln omega dash E0 minus ER. Okay, so what is omega dash ER dash means, so it is the microstate which is having the energy ER dash. Okay, it is the number of microstate that is having energy ER dash, that is the representation of omega dash of ER dash means. Okay, now we'll expand, this is using by Taylor series expansion. Okay, Taylor series expansion. So we have a general equation that is f of x is equal to f of a plus x minus a by 1 factorial f dash of a plus x minus a square by 2 factorial. Okay, f double dash of a, so like etc. We'll have the corresponding value. So at x minus a we need to evaluate the corresponding value. So this is a general representation of a Taylor series expansion. So here ln PR equal to, so this I can expand, that is we'll have ln omega dash E of 0 will be there, because this is equivalent to f of a. Okay, plus, so in the next case we'll have ER dash minus, so here this you can also write like this is proportional to ln omega dash ER dash as well. So you are actually expanding that. Okay, so that is you'll have ER dash minus E of 0 divided by 1 factorial, that is 1 factorial is 1 itself. Then we'll have f dash of a means you have to take dou ln omega dash divided by dou ER dash. Okay, dou E dash. Then you want to evaluate it is at where, because there is at x is equal to a notation is there. So like here we'll have ER dash is equal to E of 0. Okay. So you have to evaluate on this particular space ER dash is equal to E0. So you're actually expanding what ln of omega dash er dash. So once you got this one, then we'll have ln pr equal to, we can represent this representation, since this is a constant, right? So this is a constant, so this I can represent as c, and this entire representation, so I can just sort out into in this fashion, that is c minus beta dash e of r, okay, er, where beta means 1 by kt, that is equal to beta dash in this situation. Okay, so ln pr equal to c minus beta er. So here beta dash is a representation of omega dash, we can represent in this dou ln omega dash by dou e dash er dash is equal to e0, which I can represent in this case as b dash form. Okay, so we'll have corresponding representation like this. Now if I taking the exponential value of this one, taking exponential of this one, we'll have pr equal to e raised to c, then minus e raised to beta er will have the value. Okay, and where e raised to c means it will be a constant, so the probability will be equal to c into, probability will be equal to c into e raised to minus beta er. Okay, so this is the corresponding probability, and you know that the probability, the maximum probability will be equal to what? It will be equal to 1. Okay, so in this case we'll get 1 equal to sigma r c e raised to minus beta er will be there. Okay, from that representation we'll get what? We'll get the corresponding c equal to what? 1 by epsilon r, that is the value from e raised to minus beta er will be there. And now we'll actually represent pr equal to c, I can substitute here, then pr becomes, the probability becomes, so probability that is become c, I can substitute as 1 by sigma r e raised to minus beta er into sorry, into e raised to minus beta er. Okay, so that is I'll be getting the probability that is equal to e raised to minus beta er divided by sigma r e raised to minus beta er. Okay, so this is the probability of finding the energy state er. Okay, er from the above case. Okay, then what is this sigma r e raised to minus beta er? So this is we call as partition function. Okay, what is a partition function? Partition function means it is sum of all. Okay, so it is basically what? It is a representation of Qn, total number of energy state. Okay, so it is a total number of energy state corresponding to that. So we can say that it is the sum of overall states of the factor e raised to minus beta er. Okay, so that is we call it partition function Qn equal to, this is basically the total number of energy state representation we could represent like this. So you note down this probability representation, so that is more important to you further moving on. So we'll do one problem, how do we execute this understanding while do some problems regarding this one. So let me just take one question here. So here we have a N2 gas consists of a sequence of vibrating excited state with energy n plus half h cross omega, where n equal to 0, 1, 2, 3. Okay, if the level spacing, energy level spacing is 0.3 electron volt, so what is the relative population, of first excited state and ground states. Okay, if it is in thermal equilibrium at 1000 K. Okay, so N2 gas consists of a sequence of vibrating excited state with energy n plus half h cross omega, where n equal to 0, 1, 2, 3. If the level spacing is 0.3 electron volt, what is the relative population of first excited state and ground state? So if it is in thermal equilibrium at 1000 Kelvin. So in this question we are given with En equal to energy condensation is equal to what? N plus half h cross omega. So it also said that n equal to 0, 1, 2, 3. So then that means E0 equal to, we'll have h cross omega by 2, and E1 will be equal to 3 by 2 h cross omega, and E2 will have 5 by 2 h cross omega. Okay, where the difference between E0 minus E1 and E2 minus E1, that is equal to what? H cross omega. Okay, so that is the energy difference in that case, and the energy difference h cross omega equal to 0.3 electron volt. So that is we have given with the solution. Okay, so and also we have given with the temperature is at the equilibrium, so we'll have temperature that is equal to 1000 Kelvin. Okay, so actually the population of ground state, if you evaluate, okay, at the ground state where n equal to what? N equal to will be 0, so that is energy E0 will be equal to h cross omega by 2 is the energy state in that case. Okay, so when you consider the probability at this state, P0 equal to what? C e raised to minus beta E0 will be there. Okay, which is equal to C into e raised to minus beta h cross omega by 2 will have. Okay, and now, so that is a case of ground state. And Next we'll evaluate what is the case of population at first excited state. First excited state where n equal to what? 1. Okay, so that is E1 equal to what? 3 by 2 h cross omega. So we'll have the probability of finding in that case P1 equal to C e raised to minus beta 3 by 2 h cross omega will have. Okay, now what we need to find it out is that, so what is the relative population of first excited state and ground state? Okay, so relative population means we need to what? We need to take. So when you say that the relative population, okay, relative population, that means you have to take P1 by P0. Okay, so that is equal to C e raised to minus beta 3 by 2 h cross omega divided by C e raised to beta h cross omega by 2. Okay, so when you do that, C and C will get cancelled. We'll get the solution as e raised to minus beta h cross omega you will be getting here. Okay, so already we know that what is beta is. Beta is equal to 1 by kt. I already said that. Okay, so when you write into the equation e raised to minus h cross omega by kt, because beta is 1 by kt, so that is equal to h cross omega. We already know the value, that is e raised to minus 0.3 electron volt divided by kt will have the value, where k is a Boltzmann constant. Okay, so we'll get in this case p1 by p0. When you substitute the values corresponding to that, so you'll be getting p1 by p0 will be equal to 0.0308. Okay, because T already we know T is 1000 Kelvin. Boltzmann constant also we know Kb equal to 1.23 into 10 raised to. Okay, so that value you know also already know. Okay, you substitute Boltzmann constant Kb here. Okay, then you will be getting P1 by P0 will be equal to 0.0308 is the corresponding solution to that. Okay, so we'll do the next problem here. So the question number 2 here, we'll have a system has fixed number of particles n. Suppose the energy scale is shifted by eta. Okay, find the relation between new and old partition functions. So in this case, we'll have the number of particles is given as n. Okay, and you can take the energy state is er as of now, and if you assume that you have one particle, that is q1 equal to, okay, so the first function, that is the first partition function q1 equal to, we know that the representation is sigma r e raised to minus beta er. That is a representation of partition function. If you have n number of particles, that is q1n, so that is equal to sigma r e raised to minus beta er all raised to n. So this is, we call it as the old partition function here. Okay, now if you consider the new partition function, so here also we'll have the number of particles is same. Okay, so we'll have the number of particles as n, but we are given with the energy scale is shifted by eta, so that is er plus eta. So that is, we'll have q11n, that is a new one, so that is equal to, we'll have this is equal to epsilon r e raised to minus beta er plus eta will be there. Okay, whole raised to n will be the new representation. So this is our new partition function. Okay, now if you proceed with this, we'll have, we can write this one as q1 dash n. Okay, q1 dash n, that is a new function, so that is equal to epsilon r, this I can split into e raised to minus beta er raised to n. Okay, and e raised to minus beta eta raised to n, so I can split into 2. Then I can say that this q1 dash n is equal to, because this is familiar to us, this is what, this is q1n. Okay, q1n e raised to minus beta eta n. Okay, so this is the function we'll be getting. So this is a relation between old and new partition function case. Okay, so this is how we'll find the relation between old and new partition case when we have a energy scale is shifted by eta value. So it's very simple, right? So we are represented in that fashion. So the next problem, so find the partition function of two particles, okay, which can occupy any of two energy level O and epsilon. Okay, so in this case, when you find it out the answer, okay, so we'll have q1 equal to, we can take it as, that is what, epsilon r, sorry, sigma r e raised to minus beta er, so that is equal to e raised to minus beta e1 plus e raised to minus beta e2, that is the two energy levels we have. Okay, so energy levels e1 and e2 here. So it is said that O and E can occupy either one of the energy level, that is e raised to, sorry, this is not O, this is 0. Okay, so this is 0. Okay, sorry, 0 and epsilon. So in that case, we'll have e raised to minus beta into 0. Okay, plus e raised to minus beta epsilon. Okay, so that is, when you take q1 square, because two particles are there, so in that case we have to take 1 plus e raised to this will be equal to 1 plus e raised to minus beta epsilon left. So that is minus beta epsilon square will be there for two particle. Okay, so then you have a partition function for two particle system, then that is q1 square, that is equal to, we can expand as 1 plus, okay, 1 plus e raised to minus 2 beta e, sorry, e അല്ല epsilon plus 2 e raised to minus beta epsilon. Okay, so this is the value for the partition function for a two particle cases. Okay, so here 2 actually represent, it is like n equal to 2 here. Okay, so whenever you have q1 raised to n means you have to take e raised to minus beta er raised to n la. So similarly, like here n is equal to 2, so we have to take like this. So let me just do the next problem here. Question number 4, that is a system has two states with level separation. State means energy state, okay, separation of 0.1 electron volt. Find the probability of occupation of particle in each states. Okay, if the system is in thermal equilibrium, the system is equilibrium at 300 Kelvin. So a system has two states with level separation 0.1 electron volt. Find the probability of occupation of particle in each states if the system in thermal equilibrium at 300 Kelvin എന്നാണ് നമ്മളോട് ചോദിച്ചിട്ടുള്ളത്. So we'll have two probability, that is P1 corresponding to first energy state and P2 corresponding to second energy state, and will also given with the temperature, that is at thermal equilibrium the temperature is equal to T equal to 300 Kelvin. Okay, so we have given this case, and also we have given the separation of energy E2 minus E1 equal to what? It is 0.1 electron volt. So if you have two energy levels E1 and E2, so the separation between these two is 0.1 electron volt. Okay, so this one, the E1 have corresponding P1 and P2 corresponding the population at P1 and P2, and here we know that the PR, the probability representation, will have e raised to minus beta ER, okay, divided by sigma R e raised to minus beta ER is the corresponding representation. Okay, so if you do sigma R e raised to minus beta ER, that is equal to what? So you have to take two energy levels, e raised to minus beta E1 plus e raised to minus beta E2, you have to take it here. Okay, so that is in common, you have to take minus beta E1 plus E2 will be there if you take only taking this representation E1 plus E2, like that you have to represent. Okay, now let me just come to the case of first population. So that is probability of finding the case. So P1 equal to e raised to minus beta E1 divided by So when P1 equal to e raised to minus beta E1 divided by e raised to minus beta E1 plus e raised to minus beta E2. So you have to represent like that. So that is equal to, so when you represent this one, so if you divided by e raised to beta E1, if you divided the denominator and numerator by this one, e raised to minus beta E1, we'll have 1 by 1 plus e raised to minus beta into E2 minus E1 will be the corresponding value. Okay, what we have done is that we have just divided e raised to minus beta E1 on the numerator and denominator. So we'll have the corresponding value will be at this fashion. Okay, and we'll know that 1 by 1 plus e raised to beta, we know it is E2 minus E1 by kt, where beta equal to 1 by kbt, where kb is the Boltzmann constant. Okay, so from, if you substitute that into the equation, we'll have 1 by 1 plus e raised to minus, we know E2 minus E1 is 0.1 electron volt. Okay, divided by kt. Okay, and if you do so, you will have the corresponding value corresponding to that. And similarly, that means it is almost like you will be getting 0.98 or something. Okay, uh, and similarly, if you take P2, that is e raised to minus beta E2 divided by e raised to minus beta E1 plus e raised to minus beta E2. Okay, so that is, once you divided with the E2, e raised to minus b E2, you will have 1 by e raised to beta E2 minus E1 plus 1 will be there. Where T, we already know T is 300 Kelvin. Then you have to substitute the Boltzmann constant, that is 1.38 into 10 raised to minus 23. I think, hope I am correct. Okay, so that is Boltzmann constant. Okay, then here we'll have 1 by e raised to beta E2 minus E1 plus 1 will be there when you divided e raised to minus beta E2 on the numerator and denominator. So okay, now if you do here, that is 1 by e raised to zero point 0.1 electron volt divided by beta means kbt. So you have to substitute kbt plus 1, that will be getting the value 0.02 will be the corresponding value that you will be getting from here. Okay, so we got the population at a two stage. One is 0.98, another one is 0.01 from the case. So here you can see that the total separation in this case will be equal to 0.1. So that is equal to total 1 will be the probability. You can see the probability of P1 and P2. Okay, so the total probability, if you calculate, that is PR equal to P1 plus P2. So you will be getting what? 0.98 plus 0.02, you will be getting 1. Okay, so that's why. So this is a exact representation of what we have done here, because we know that ultimately the maximum probability is getting 1. Okay, so in this probability of getting 2 is 0.02, that means 2 percentage. Okay, and probability of getting this stage, that is 98 percentage. Okay, so that is in total, if you combine that, you have to get, basically you have to get the value 1. Okay, so that is the about the different problems regarding partition function. So we have done almost 4 problems, and also we have find it out the probability relation in terms of partition function. Okay, and also we have introduced what is canonical ensemble is. It is a collection of microstate which having nvt as the constant number of particle, volume and temperature. Okay, so from that representation we'll identify the partition function. Okay, in the next class we'll discuss about the statistics of a or statistical quantity in the canonical ensemble case. Okay, and after that discussion we'll move on to the discussion of harmonic oscillator problem and ideal gas problem using canonical ensemble theory. Okay, so with that I'll be winding up this session here. Thank you.